So heat waves in general are now a very hot topic. Haha, you see how I made a pun out of it. So obviously tropics are getting a lot of attention, but even the mid latitudes are getting lots of heat waves these days, especially 23, 24, which have been record warm years. We are waiting for 25 to see whether it will be a La Nina or will it become a El Nino. Is the pattern that we are seeing is even a La Nina and so on. The basic question of tropics becoming too hot to live because the humidity and wet bulb temperature going up, and thus limiting the body's ability to cool down by sweating and losing the heat through evaporation, because if the air becomes too hot and humid, then the body cannot really evaporate if the air is close to being saturated and so on. This is a nice paper that addresses this issue and provides a very nice result with some theoretical background as to how this has to work. My favorite scientist is on this as well, Isaac Health. Projections of tropical heat stress constrained by atmospheric dynamics. This is very important. Extreme heat under global warming is a concerning issue for the growing tropical population. We cannot deny that part. However, model projections of extreme temperatures, a widely used metric for extreme heat, are uncertain on regional scales, and Tim Palmer and others have discussed this a lot, saying the current IPCC models are not producing very useful information, especially because the first couple of decades are dominated by internal variability model uncertainties, and beyond that it's all scenario uncertainties. In addition, humidity needs to be taken into account to estimate the health impact of extreme heat. Here we show that an integrated temperature humidity metric for the health impact of heat, namely the extreme wet bulb temperature, is controlled by established atmospheric dynamics and thus can be robustly projected on regional scales. So if you have large scale atmospheric dynamics that can reliably tell you what will happen on regional scales given a level of warming, then that can be very useful to see whether we'll really reach deadly humid heat stress levels. For each 1 degree C of tropical mean warming, global climate models project extreme TW, the annual maximum of daily mean or 3-hourly values, to increase roughly uniformly between 20 south and 20 north latitude by about 1 degree C. That is wet bulb temperature increasing by 1 degree C for 1 degree C warming. This projection is consistent with theoretical expectation based on the tropical atmospheric dynamics and observations over the past 40 years, which gives confidence to the model projection. Okay, for a 1.5 degree C warmer world, the probable 66% confidence interval increase of regional extreme TW is projected to be 1.33 to 1.49 degrees C, whereas the uncertainty of projected extreme temperatures is 3.7 times as large. These results suggest that limiting global warming to 1.5 degrees C will prevent most of the tropics from reaching a TW of 35 degrees C, the limit of human adaptation, as has been reported in several papers now. And then the question has been whether we are going to hit this limit anytime soon. That's where these constrained projections become really important. So there are multiple ideas here. 1.5 degrees C very likely will surpass it. We may have come very close to passing it in 2023, 24 maybe, but it's not clear what will happen in the coming years. If you look at the past, such extreme jump out years have happened, but then they have cooled down in the following years. So now we wait eagerly to see what happens now into 25, 26 and so on. Well, we'll read some text here because it's really important for the context, and then we'll look at some figures. The impact of global warming on local extreme heat is projected to be detectable earliest in the tropics, where baseline temperatures are already high. In addition, countries located between 20 south and 20 north latitude will soon become major contributors to the global population growth, and there is thus a pressing need for accurate projections of extreme heat in the tropics down to regional scales, and ultimately you even want it at local scales, especially the early warnings, not the projections. The most widely used metric for extreme heat has been the extreme temperature. However, projections of extreme temperatures have large regional uncertainty arising from insufficient model representation of important land processes, because on land, the local land use and vegetation, urbanization, irrigation, etc. play a critical role. Moreover, to facilitate the estimation of heat-induced health impact or heat stress, the effect of humidity should also be included. This is because the major way for humans to lose metabolic heat in hot weather is evaporative cooling, as I mentioned, what we call sweating, the efficiency of which anti-correlates with humidity. In particular, the inclusion of humidity is necessary for assessing heat stress in the tropics, the warmest and the most humid places on Earth. The importance of humid heat has been increasingly recognized, of course. Studies have shown that increased humidity with temperature following the Clausius-Clapeyron relationship can worsen the heat stress in the tropics, while other work has noticed a reduction in either relative humidity or specific humidity on the hottest days, which is not limited just to the tropics. Okay, Clausius-Clapeyron, of course, is the exponential dependence of humidity on temperature. Given the possibility that humidity can interact with temperature in extreme heat, it's necessary to better quantify and improve our mechanistic understanding for the control of humid heat. Here we used the extreme wet bulb temperature TW, an integrated temperature humidity metric for heat stress. You can look up the methods for how they do it. TW by definition is the lowest temperature that human skin can be cooled to through evaporation of sweat. Therefore, the closer TW is to the upper limit of human skin temperature, which is around 35 degrees C, the more intolerable the heat is, with a survival limit of TW equal to 35 degrees C, which was raised by, I think, Tara and Takabi, or maybe El Tahi, you can look it up. The reference number is here 16 from the paper. So here high TW values below this survival limit also have adverse health impact. So it's not like nothing happens till 35 and then suddenly you go kaput, but many exacerbations of pre-existing conditions can happen, including cardiovascular diseases, COPD, and so on. Furthermore, TW is a major component in the wet bulb global temperature, which is the standard metric for workplace heat stress, which looks at heat directly under the sun versus in the shade and so on. In this article, we argue that regional extreme TW in the tropics is controlled mainly by robust atmospheric dynamics that have been established previously, rather than by local processes that are more uncertain. Therefore, tropical extreme TW can be robustly projected on regional scales under global warming using this large-scale atmospheric dynamics constraint. Okay, what are the model projections doing? We will look at the figure in a minute, which shows the projections of extreme TW or TW max and extreme temperatures themselves, Tmax, by 22 global models from the coupled model in comparison project CMIP 5 under the representative concentration pathway 8.5, which is the worst case business as usual scenario. Okay, TW max and Tmax here refer mostly to the annual maximum of daily mean values in this paper and refer to the annual maximum of 3 hourly values when specifically stated. The multi-model mean of Tmax averaged over tropical land within 20 south, 20 north warms faster than the tropical mean temperature when you include ocean. However, TW max closely follows the tropical mean warming, similar to an earlier finding using an atmospheric model coupled to a slab ocean. Some details there. If you couple the entire ocean, then the processes are very slow, but integrating forward with just the slab ocean, which has certain constraints on how heat has to be transported out of the tropics towards the poles and so on, allows you to make some simulations faster and still get the insights you want to get if you design it properly. These results also hold when analyzing 3-hourly data that resolve diurnal cycle from 2 models. So we will look at figures which show Tmax and TW max trends for all locations normalized by the tropical mean warming under business as usual. Tmax warming is spatially inhomogeneous over land ranging from 1 degree C to 2.3 degrees C for each 1 degree C of tropical mean warming, consistent with the previous findings. Okay. By contrast, we find that increases of TW max have no notable land-ocean contrast, ranging from 0.8 degrees C to 1.3 degrees C for each 1 degree C of tropical mean warming. So, if some details there you may want to pay attention. So, increases in TW max do not show land-ocean contrast, but Tmax do because of the heat and humidity combination that is less variable in this sense. Using the annual maximum 3-hourly TW for TW max does not change this result, so they are fairly robust. In reality, just dealing with heat waves, you may need 3-hourly temperature predictions, early warnings, etc. The spatially uniform TW max trend is not a cancellation of errors among different models. Instead, all models show good agreement on TW max trend, even down to regional scales. So let's look at figure 1 before we go on. Oh, what did I do? Figure. I just completely skipped it like an idiot. I do this too often. Figure 2, 3, not a smart move. Okay, so let's put figure 1 right here after this slide. Let me pause and okay, so I fixed I don't know, I always end up doing some silly things because I don't check the PPT properly before starting the podcast. But anyways, here we are with figure 1, TW max and Tmax trends in climate models under RCP 8.5 business as usual. We are looking at multi-model mean time series of the tropical mean, so 20 south, 20 north temperature. T-bar is in the cyan here, and TW max over land is shown here. So the tropical mean and maximum are closely following each other, but if you go to this is Tmax land here, which warms faster than the average, but TW max land tracks it fairly closely. As we said, land-ocean contrast is not large in this case. If you look at specific models 3-hourly into the future, so this is going from 1980, so up to here you have observations and then you have projections going forward. So there are 2 models here which are looking at the TW max and Tmax trends for business as usual. So land mean Tmax, land mean TW max, as we said here. B and C are the same as A, but using annual maximum 3-hourly values. So the results are similar. So the magnitudes are slightly different. This is similar here, but this is lower here. Okay. Nonetheless, keeping that in mind, D and E multi-model mean location specific Tmax and TW max trends normalized by the tropical mean TW bar. Okay, what do you see? You see some hot spots here in terms of the this is a non-dimensional number because it's been normalized, but you can see the local warming regional scales is higher than the global tropical average, just as we saw here, and Middle East and Sahara show up. India remains, if you look at the trends, it still remains cooler than most regions around, but then there is a seasonality that you have to worry about. There's a hotspot here, and if you look at normalized trends of TW max instead of T max, you see that now the numbers are lower. Obviously Tmax tends to be much higher, as we saw here as well. So the temperature warms, humidity Tw better not be as warm as Tmax, because otherwise we'll start dropping dead, right? So where was I? Let's go back here, projection. So let's come back to the text. The spatially uniform TW max trend is not a cancellation of errors, as we said. Figure 2 shows the model spread of Tmax and TW max projections for 4 selected regions that have caught substantial attention in the literature. The Amazon rainforest, because the forest may die and become a carbon sink, carbon source, and may have positive feedbacks to the global climate. The maritime continent, which is already very hot, and that's the boiler box, where about 5 meters of rainfall every year. The Indian Peninsula, which is getting a lot of attention because they think people will start dropping dead like flies, and of course the Sahel. The projected Tmax warming has large spread among models, which is especially prominent in the Amazon rainforest, consistent with earlier analysis. However, for regional TW, all 22 climate models project a close 1-to-1 ratio with the tropical mean warming. Using the annual annual maximum of 3-hourly TW does not change the results, as we saw. Intriguingly, the model spread of Tmax tends to grow with the amplitude of the projected warming pronounced for the Amazon rainforest and maritime continent. So if you use different scenarios or different models which project different levels of warming, as the warming increases, the Tmax also increases in terms of the spread between the models and in the model itself in terms of ensemble members. Okay, so the model spread of TW max does not show evident growth within the range of simulated warming up to roughly 4 degrees centigrade for RCP 8.5 by 2100. That the intermodal spread is much less for TW max projections than for Tmax is also true for other tropical land regions. To summarize, global climate models predict that TW max will increase roughly uniformly in the tropics by about 1 degree C for each 1 degree C of tropical mean warming. TW max will also increase by 1 degree C if tropics overall averaged warm for 1 degree C. Does it make sense to average over the whole tropics? That's where the dynamic constraints come in. Models show a wide spread on regional Tmax projections, but agree very well upon regional TW max. And the argument is that these are not cancellations of errors, that this is real dynamic constraint. So how is the theoretical support What is the theoretical support then? For a theoretical projection of TW max, we argue that tropical atmospheric dynamics exert a strong tropics-wide control on local TW max. This control is through the functional relationship between TW and the moist static energy. If you don't know what that is, you can look at other podcasts that I have, which is a variable regulated by atmospheric dynamics. In the tropics, the free tropospheric temperature is roughly uniform in the horizontal as a result of weak effect of Earth's rotation. It's called the weak temperature gradient. Dynamics basically smooths out the gradients very quickly over the tropics, and the adjustment timescales in the atmosphere are relatively rapid. This horizontally uniform temperature, which is determined by the near surface moist static energy in regions of deep convection, sets the upper bound for MSE at all locations. Indeed, the maximum near surface MSE is roughly uniform within 20 south, 20 north, even more uniform than the time mean MSE. Okay, so there are some details there. Maximum near surface MSE is uniform and even more uniform than the time mean MSE. And the spatial, basically you can imagine in a simple sense that tropics have a lot of convection and there are sinking regions. If it's very strongly rising motion over the maritime continent, you have sinking region in the eastern Pacific, western Indian Ocean, and so on, and there is a meridional branch as well, Walker cell, Hadley cell. But mainly when there is heat and convection happens, the convection, which is moving moisture energy very rapidly, is going to spread it out and make the temperatures very rapidly uniform. So MSC itself is uniform in that sense. And the spatial pattern of TW max closely follows the uniformity of the maximum MSC. There are a lot of nice supplementary figures that you can look up. As this upper bound for near surface MSC and equivalently for TW is a common one over land and over the ocean, we expect that changes in TW max should also be roughly equal over land and over the ocean under global warming. So delta TW max over land is approximately equal to delta TW max over the ocean with warming. What is the change in TW max? Equation 1 thus provides a handle on TW max over land, which is challenging to predict due to various land types and land processes, as a theoretical projection of TW max over the ocean can be made relatively easily. It's a uniform surface and varies slowly. Near the ocean surface, air is close to saturation and TW changes are approximately equal to temperature changes, exactly equal when air is saturated. Delta TW max ocean is thus approximately equal to the change in the warmest sea surface temperatures. Thus, 1 degree C of delta TW max on land is accompanied by 1 degree C of warming of the warmest SSTs according to equation 1. So it's a nice constraint they have developed. Furthermore, the area dominance of the ocean and the relatively constant shape of the SST histogram under global warming together result in a 1-to-1 correspondence between warming of the warmest SSTs and the tropical mean temperature. While there is potential for differences between changes in these relatively warm SSTs and the tropical mean SST, we find these differences to be small enough that they do not undermine the theoretical considerations here. We thus expect delta TW max land roughly equals the tropical mean warming. Global climate models shown in figures 1 and 2 are consistent with the preceding theoretical considerations. For each 1 degree C of tropical mean warming, models on average give 1.05 degrees C of delta TW max on land, 0.93 degrees centigrade of delta TW max on the ocean, and 0.91 degrees C of the warmest quartile mean SST increase, all close to 1 degree. So the non-local control of TW max by the warmest SSTs can be at odds with the perception that these extreme events are driven by rare local meteorology, and thus controversy deserves some clarification. How does it happen? While TW max events are driven by local processes, the potential magnitude of TW max is largely set by the uniform free tropospheric temperature. So you can create a local spike, but the potential magnitude is set by this larger scale constraint. The effectiveness of this non-local control is evident in the uniformity of TW max increases in figure 1E, which we looked at here. Right, they're relatively uniform, right, compared to the hotspots in Tmax. That's really important result. Okay, the effectiveness of this non-local control is evident in the uniformity of TW max increases in figure 1E and the good agreement across models in figure 2. I will show that in a minute, neither of which can be explained by the heterogeneity of local processes. Moreover, the existence of such a non-local control within the tropics also explains why the tropics are consistently warm and humid, but the highest TW and WBGT, wet bulb global temperature, are observed in the subtropics and not in the tropics. These considerations thus support the picture that the magnitude of delta TW max across tropical land regions is set by the warmest SSTs and not by local processes or the spatial pattern of SST, which is remarkably good, because it could also mean that the biases in the models in SSTs and their patterns may not be that important when we go after TW max. Okay, so here are the model agreements on regional TW max projections. Again, we are looking at T max and TW max and the one-to-one theoretical line, and you can see they're all on the same 1-to-1 line, with Tmax being higher as we expect. This is for the Amazon rainforest. This is the tropical mean warming and the change in extremes, and the same thing here for maritime continent. The difference is not as high as the Amazon. Change in extremes over the Indian peninsular region, again you can see similar behavior. The exact growth in TW max with warming is different, but you can also see the spread increases as we already said before, and this is for the Sahel region. Okay, so the scales are the same, but you can see that this warms the most, this and this are similar, they are all similar here. The differences are different, you know, this is not as different. It's a very wet region with rain throughout the year, and these are dry. This is relatively dry, and this is wet and humid based on the season. Okay, so this is TW max in observations and reanalysis. I'm not going to go into the detail, but basically the argument is that if you compare the distributions, regression, slope of TW max against global tropical mean warming in terms of degree C per degree C, probability density function models with RCP 8.5 here, if you detrend them, the line comes down to here in terms of the regression slope, and this is the reanalysis. So basically they are doing relatively well even in the historical simulation. So you can trust this change in the probability density distribution with the warming, and that's basically the argument, that we have some constraint on these things. So main message is still the same. So to jump ahead, what do they say? While we do not attempt to formulate an attribution statement for the TW max trend over land seen in figure 3a, this one, we note that the tight relationship in the overall trend as well as higher frequency variability strongly suggests that any attribution statement for the tropical mean or SST can also be applied for TW max, which is what we are worried about in terms of tolerable heat stress, right? What are the implications for the future? I also skipped another figure 4 here, so let me see if I need to include. Never you mind, there is no figure 4. I somehow thought there is. Okay, let's read the implications and then conclude. Implications for the future climate then. Consistency of model results with the theory and observations lends strong support to the capacity of global climate models in properly simulating regional TW max increases. Oops, give me a second, I have okay, I better wrap this up. It's been interrupted too much. Okay, so what are the implications? Models can be trusted because they are doing fairly okay in terms of simulating the TW max increases. In a 1.5 degrees C warmer world, the projected 66% confidence interval, equivalent to the Intergovernmental Panel on Climate Change's likely range for TW max, increases across all tropical land regions over 20 south, 20 north, and that number is 1.33 to 1.49 degrees C. So that is for 1.5 degrees C warming with 66% confidence level, and this is consistent with simulated tropical mean warming of 1.4 degrees C in a 1.5 degrees C warmer climate. So some details. So there is a figure 4. What the hell did I do? Oh, sorry folks, I'm really not doing well today. Yeah, sorry, but I remembered when I read the paper there was a figure 4, but when I went back to look for it in the PDF, you know, you hit the arrow and then it jumps and then you can miss part of the page, which is what happened. Wow, stupid excuse, but nonetheless you get the point by now, I suspect. So projected Tmax increases have a wider distribution, the absolute relative standard deviation of which is 3.7 or 1. So absolute standard deviation of which is 3.7 times that of TW max increases. The reduction in uncertainty is more pronounced for regions where TW max projections are most uncertain. For example, in the Amazon rainforest and the maritime continent, the absolute uncertainty of Tmax increases is around 4 times that of TW max increases. So so you can see here maritime continent is here. You can see how the range of uncertainties covers. These are slightly separated here, but here they are all pretty close to each other. Some details that I am not going to worry about. Okay. Yeah, so therefore 1.5 degrees C or 2 degrees, our results imply that global mean warming will have a proportional effect on the regional TW max in the tropics. One main message. The maximum 3-hourly TW era interim result ever experienced in the past 40 years is by 99.98% of the land area within 20 south 20 north is below 33 degrees centigrade. That's wet bulb maximum temperature. Therefore, a 1.5 degrees C or 2 degrees C warmer world will likely exempt the majority of the tropical area from reaching the survival limit of 35 degrees C. Okay, if we keep even 2 degrees C warming, global warming to 2 degrees C warming. However, there exists little knowledge on safety thresholds for TW besides the survival limit, and 1 degree C of TW increase could have adverse health impact equivalent to that of several degrees of temperature increases. So we cannot just discard it, but we should at least stop yelling about deadly TW or humid heat reaching to be. We should stop yelling about the dangers of reaching the survival limit of heat stress. TW will thus have to be better calibrated to health impact before wider societal implementation. Nonetheless, the confidence in TW max projection provided in this work still raises the confidence in the projections of other calibrated heat stress metrics that account for TW, such as the wet bulb global temperature. As I said, it's a more sophisticated measurement of direct sun exposure versus shade and so on. So this is just showing that the tropical mean warming here of 1.4 degrees C for a 1.5 degrees C warming shows you a TW max that is here and T max that will be much more spread out. So we will get a warming of around, even if we keep the maximum warming to 2 degrees C, we will get long tails of maximum T max, but TW max will be centered here at around 1.4. So it's, in some sense, there is good news, and I wanted to include it just because there is a lot of discussion on this topic and we have to be careful. It doesn't change anything in terms of adaptation and mitigation. We still have to go ahead with it. The science has still to be used when we make claims. So often I'm worried that we are kind of abandoning science in some of the claims we make, especially considering the uncertainties in the projections out to 2100, which are basically dominated by scenario uncertainties after you go beyond a couple of decades. And if you look at all the geopolitics that is going on now with Russia, Israel, Hamas, Ukraine, tariffs and so on, if we already got the range of projections, then maybe we need to focus more on what would happen in the next 10 years or 20 years, which is where the models are showing, much more handleable uncertainty. Okay, I'll leave it there.